So in this video I want to go over these examples on how to use the limit definition of the derivative in order to find the slope of the tangent line to a function at a certain point. And in these first examples we're using the formula f prime of x, or the derivative of y with respect to x, which refers to the rate of change of the y variable as x changes. And the way this works is it's f of x plus delta x minus f of x all over delta x, and the limit of that expression as delta x approaches 0. So in example number 6 we have, instead of f, we're working with g, and there's a couple of ways that this can be done, but we'll start it off like this. We're looking for the slope of the tangent line to the graph g of x equals 3 halves x plus 1 when x is equal to negative 2, and we're going to call that g prime of negative 2. And we're going to set it up in exactly the same way we set up the formula above. We have the limit as delta x approaches 0 of g of negative 2 plus delta x minus g of negative 2, all divided by delta x. At this point we're going to plug in. We still have the limit as delta x approaches 0. G of negative 2 plus delta x means to take the g function and wherever you see x, replace it with negative 2 plus delta x in parentheses. And since g of x is 3 halves x plus 1, we're now going to have 3 halves negative 2 plus delta x plus 1. Now that part is only g of negative 2 plus delta x. We still need to subtract g of negative 2, and so I'm going to put that in parentheses, and I'm going to replace the x with negative 2. So I have 3 halves times negative 2 plus 1, and that's going to be my whole numerator all over delta x. Now we're going to simplify that up a little bit. Limit as delta x approaches 0. I'm going to now distribute the 3 halves times the negative 2 plus delta x, and 3 halves times negative 2 is negative 3, then plus 3 halves delta x, then plus 1, then in parentheses I'm going to have 3 halves times negative 2, which again is negative 3, plus 1 is negative 2, but I want minus negative 2, so that's going to give me plus 2. Once again, that's all over delta x. Simplifying that numerator up, I have the negative 3 plus 1 plus 2. Those are like terms. I can't add the 3 halves delta x to that, but those are all going to go away. And I will simply be left with 3 halves delta x over delta x, at which point the delta x's can cancel, and I'm going to be left with 3 halves. And that would be my final answer. Now what you should notice here is that that 3 halves is the same as the slope of the original function. And what we've said here through this long process is that the slope of that line when x is negative 2 is just 3 halves. Well, the slope of a straight line is going to be the same or constant at every x value in the domain. And that's the basic property of a straight line. It has the same slope everywhere. And we just demonstrated that. Now when we use something that's not a linear function, then we're going to get a different value for every x value that we use. But this is showing us the rate of change of that function, 3 halves x plus 1, when x is equal to negative 2. And in this case, it is the constant 3 halves, which is the same as the slope of that function. And we'll continue in the next video with the next problem, which is no longer a linear function, but we'll set it up and we'll execute it the same exact way that we did with this one.